is figuring out what is the pattern for our entire data set. So if we look closely at an individual's data, this is what we're seeing here, where we have one record, which contains the exact location of whether there was a tree here with the letter M or no tree. Okay, and so if we reveal this training data point, then we can identify sort of sensitive information, which is here the location of each of these trees. What we're going to do to obtain privacy is we're going to randomize the record that the individual submits. And so one way to do this is to say, we're going to ask the user to first flip a coin that's slightly biased. And then based on the outcome of that coin, the user is going to either report the true answer, whether there was a tree or not, or is going to flip another coin and report a random answer. And so what we obtain is this record here, which is a little bit noisy, right? You can see some of the trees that were here are still in the report, and some of the trees that were not here have been added by the random effect or removed by the random effect. But if we patch all of these reports together, then we get this new noisy view on the data where you can see that the picture clearly still is visible. We can still identify the overall pattern, despite the fact that each sort of user record now has some plausible deniability that there was or was not a tree in a specific location. So we're able to preserve privacy at the individual level while still benefiting from the data at the global level of the data set. And so this is really the metaphor for why privacy preserving machine learning is possible, because in machine learning, we care about the patterns that are found across multiple training records, not individual features of a specific record. And so we can learn with privacy despite the constraints that it adds. So the first way that we can train a model with privacy is based on stochastic gradient descent, which is applicable to pretty much any model that is differentiable. And so what we do typically in stochastic gradient descent is that we first sample a mini batch of training examples, and then we're going to compute the average error of our model on these training examples, so the loss, take the gradient of that loss with respect to the parameters, and then apply this gradient to update the model parameters in that direction. Okay, and so if we do this iteratively, we eventually obtain a model that is a good predictor on the test set. If we want to do this with differential privacy, so some of my colleagues introduced this approach, which is differentially private stochastic gradient descent. We're going to make two minor changes to the way that we perform gradient descent. The first change that we're going to do is we're going to clip the gradients, and we're going to compute these gradients on a per example basis. So you can see here that before I was computing the average loss and the average gradient. Now I'm computing the per example loss and the per example gradient. What this means is I know each contribution from each training example to our model update. I'm going to clip each of these gradients to limit how sensitive my learning algorithm is to the training data, and then add noise to the average gradient before I apply it to protect privacy. And so if I do this, these two simple modifications, I get a version of stochastic gradient descent that is differentially private, right? And so this is, we can deploy this, and we've done that on a wide series of models from different domains. But one issue that comes when we apply this approach is that typically it will harm the utility of our model. So we'll notice that there is a lower test accuracy for the differentially private model than for a non-private model. So we started investigating this from multiple angles. The first one is sort of, I think, which opens up a lot of future work, which is, are we using the right architectures to learn private models, right? Because what we've been doing so far here, and it's suggested by sort of how I presented this algorithm, is we take models that are trained without privacy, we substitute with a privacy-preserving optimizer and retrain the model. But what this means is we've done all of the architecture choices based on the non-private training runs, and then now we're just assuming that by changing the optimizer into a differentially private optimizer, we're going to obtain a model that is the best possible privacy preserving model. And so this is actually something that is incorrect. So what we've noticed in particular is that if we look at what happens to our activations internally within our neural network when we switch to differentially private stochastic gradient descent, is that the activations of our model explode, okay? And so this is problematic because it eventually impacts our ability to learn from the data and to converge to a solution that has high test accuracy. So in follow-up work, what we've been looking at is whether we should replace some of the activation functions that we've chosen for our models with different choices when we're learning with differential privacy. And this makes a lot of sense because if you look at how deep learning has progressed, one key component is to use sort of piecewise linear activation functions like ReLU, for instance. And so if you look at a ReLU, it makes it hard to estimate how sensitive your learning procedure is to the training data because the ReLU is completely unbounded in the positive axis. And so here, what we're looking at is what if we were to design architectures that use bounded activation functions when learning with privacy? And so we found that this is very useful. In particular, we use this family of activation functions called tempered sigmoids, where what we've done is we've sort of done a hyperparameter search because this is a whole family of activation functions. So we can explore different variants of this bounded function. And we found that there is a regime where these bounded activation functions significantly outperform the ReLU activation function when learning with privacy. For a fixed privacy guarantee, we get significantly higher accuracy. And so this is very interesting. And in particular, we can look at sort of the training convergence. And as we increase the privacy budget, so as we train our model for longer, you can see that here, if we use a bounded activation function, here we've taken a particular example of our family of activation functions, which is the 10H. And you can see that the 10H consistently outperforms the performance of the ReLU throughout training. And in fact, it converges significantly faster early on in training, which makes it very difficult for the bounded activation to training run to sort of catch up to the same utility levels. And so if we look at what happens internally, of course, because now we have used the bounded activation function, this prevents the activations from exploding. And so this better predisposes the gradients to the clipping operation because the gradients themselves depend on these activation norms. And so when we put all of this together, this allows us to improve the state of the art in terms of using differentially private stochastic gradient descent on a couple of benchmarks. This is work we actually presented at PPAI this year. And so you can see basically on MNIST, Fashion MNIST, and CFAR, the improvement is significant. So from 96 to 98.1, 82 to 86, and so on. And this is sort of equivalent to sort of several years of improvements in the analysis. And here we're getting this with a simple line of code that needs to be changed. So this, I think, shows the value of asking ourselves the questions of whether we're making the right choices in terms of the architecture when learning with privacy. So another angle that we can explore in sort of understanding why sometimes learning with privacy has an impact on the utility is we need to think about what privacy does to our distribution of data, right? So typically, if we look at data sets, we have points that are very outlier points to the distribution, where we have sort of tails in the distribution with very weird, non-prototypical examples of our task. And then as we go sort of closer to the mode, we have very prototypical examples of the different classes that we're trying to learn from. So here I've illustrated this with the handwritten digits. And so what happens when you learn with privacy is that the more privacy you have, the less you're able to learn about the tails of the distribution. So here, if I go back here, this is sort of the hardest to learn with privacy, somewhat hard to learn with privacy, and the easiest to learn with privacy. And so we can actually see this in practice in sort of concrete applications of differentially private learning. One of my students, Vinith here, has been looking at this in the context of healthcare data. And what he found is that differential privacy has a significant impact on the utility of healthcare models because of the way that the healthcare data is collected. It has significantly heavy tails in the distribution. And of course, the data is very imbalanced, fortunately, because there are very few sick people. And so this makes the impact of differential privacy on these models much more significant. And so this is what is shown in this table here, where you can see that the performance is much lower when learning with strong privacy guarantees. And so the interesting thing about this work is we try to understand why is this the case, and can we explain sort of what is going on under the hood. And so Vidith looked at essentially the connection between this lack of utility and a certain lack of fairness in the predictions that are being made. And in particular, he found that when learning with privacy, we are significantly giving more influence from the majority of the patients, so patients that are in the majority class, on the model that we're learning. Whereas if we hadn't learned with privacy, patients that are in the minority would have had more influence on the model that we learned. And the fact that they had more influence on the model explains why the model performs better, because again, these cases in the minority are typically the most interesting in terms of the healthcare task that we're trying to solve. And so this raises an interesting question of whether there is a possible tension between accuracy, privacy, and fairness. Okay, so in the interest of time, I'm going to go to the second flavor of privacy that I wanted to discuss today. And really here, the idea is simple, is to benefit from the aggregation of multiple models to infer with privacy. So here we're not changing out all the way that we train the models. What we're doing is we're training an ensemble of teacher models on disjoint sets of data. So these are partitions in the mathematical sense. There is no overlap between the points in the different partitions. And so once we have this ensemble of teacher models, the question is, how do we ask them to predict while preserving privacy? The naive thing you can do is just take the votes that each of these teachers are going to make for the different classes, build a histogram, and return the class that received the most number of votes. This provides privacy in the sense that when you have a consensus among these different teachers, it makes sense that the label that they predict is private because it has been predicted multiple times independently by different models trained on different subsets of the data. But there is sort of a couple of edge cases, especially when different classes here receive about the same number of votes, where a small number of teachers and sometimes one single teacher can change the outcome of the aggregation by flipping their vote from one class to another. And so to protect differential privacy, we have to add noise to the histogram before we take its argmax. And so this is a very well-known mechanism in the differential privacy literature known as the noisy argmax. Once we do this, we have a differentially private API where what is going on here is that if we ask this noisy aggregation for a label, the label that's being predicted comes with differential privacy guarantee. And so we can reveal it without fearing that some of the data here that is private is going to leak. The problem with that mechanism is that every prediction that we make, although it has bounded privacy leakage, the privacy leakage is non-zero. And so what this means is as we make more and more queries to the ensemble, eventually the privacy guarantees that we're able to prove degrade. And so to alleviate this problem, what we're doing is we're using public unlabeled data to transfer the knowledge acquired by the ensemble of teachers into a student model with knowledge transfer techniques or semi-supervised learning. And so what this means is that we can deploy the student model. The student model is going to predict, and the privacy budget will be fixed after we've trained the student model. The number of queries it has made to train itself is going to bound the total privacy cost. And after that, we can even discard completely the ensemble of teachers since we have all of the knowledge we need in the student. The very exciting thing about PPAI and why I wanted to discuss it today is that it shows very well that there is alignment between differential privacy and machine learning's goals. So in differential privacy, you can think of it as sort of a worst case variant of generalization, which is average case. And this shows very well in PPAI because when teachers agree on the prediction, it is more likely to be a correct prediction because it has been made multiple times independently. And so you get this notion of generalization. But it is also more, it's easier to protect the privacy of this prediction because when there is a large consensus within the teachers, you can add more noise to the histogram before you take the argmax. So you can prove tighter differential privacy bounds. And so what this means is we've actually exploited this observation, and we've introduced a variant of PPAI where we only reveal the predictions of the ensemble when the ensemble has very significant consensus among the teachers. And this means we can answer more labels where each label is answered at a smaller expense in terms of our privacy budget. And these labels are also more likely to be accurate. So this is very unusual in sort of computer security research where the privacy goal here is directly aligned with the performance goal of the machine learning model. The third flavor that I wanted to discuss today is a variant of PPAI that we've recently proposed and is going to appear at ICLR later this year. And so here the idea is to take PPAI and realize that this mechanism here is very well suited for distributed learning, right? Where you can imagine here, I've told you that we can train all of these teachers on subsets of this large data set, but in some settings, there might actually be different data sets here that are already partitioned and hosted by different parties. And so each of these parties is going to have their own machine learning model that they've trained on their own local data set. And so the question is, can we use this PPAI mechanism to allow these different parties to collaborate and to do this inference in a fully distributed manner? And so the answer is yes, as long as we throw in a little bit of cryptographic primitives here to make the process confidential. So we came up with this protocol called CAPC, so Confidential and Private Collaborative Learning, that extends the differential privacy guarantees of PPAI with confidentiality guarantees. So let me first walk you over the protocol and I'll explain why these guarantees are interesting. So the first step is that one of the teachers is going to act as the student here in this PPAI setup. So one of these teachers here is going to play the role of the student. This querying party, so this is the student, sends the encrypted sends the input that they'd like the other parties, the other teachers to predict on in an encrypted way. And so this is, for instance, a test input or an unlabeled input that the querying party would like help labeling from the different parties. So one good example of this is if you come back to the healthcare motivation that I discussed earlier, if you have different hospitals, you can imagine that they have sometimes patients that come in that are sort of unusual compared to the distribution of patients that they have seen so far in the hospital. And so they might not have the right training data for their model to predict on this patient. And so here what they're doing is asking other hospitals for their opinion on this specific patient. So the data is sent encrypted so that the hospitals, the responding parties, are unable to read, of course, the input that they're predicting on. To be able to predict on, we use homomorphic machine learning, which means that each of the responding parties is going to produce a logic vector that they produce without reading the input that they're predicting on, but also without revealing the model that they're using to predict to the querying party, which is also a very nice property. So once each of the answering parties has predicted a logic vector, what is going to happen is that the querying party is going to engage in a two-party protocol with each of these answering parties to first turn this logic vector into a one-hot vector to get the vote corresponding to the answering party's prediction. And then the answering parties are going to send each of their shares to a trusted third party, which is going to aggregate all of these answering party shares to essentially reconstruct the histogram that I mentioned in Pate. And then this trusted third party can add the noise to the histogram required to obtain differential privacy, and then engage in one final two-party protocol with the querying party in order to obtain the label that was produced by the noisy argmax. And so what you can see here is that then the querying party receives the label that the ensemble of teachers predicted. But what's interesting is that the querying party did not have to release their input to the answering parties. The querying party did not see the models that the answering parties are using. And the answering parties get a differential privacy guarantee that there is bounded leakage from their own personal training sets to the querying party. And so this provides a very nice set of properties, which means that these models can now collaborate with the sufficient trust because they have both these confidentiality guarantees from the use of crypto and the privacy guarantees from the use of Pate. Okay, and so this is very nice because it also allows you to produce sort of active learning scenarios where you can imagine that the querying party is going to use that label to improve their own local model over time. And this is something that we've demonstrated in the paper. In particular, it helps with fairness. And so one thing that I want to comment on before I move on to the last part of the talk is that this is a very attractive alternative to federated learning. So federated learning has serious limitations. In particular, it assumes that there is a central model that is sort of trained by aggregating updates from many participants. So this means that you need to trust the central party into maintaining this central model and receiving the aggregated updates from different participants. Of course, the participants in federated learning do not get any privacy guarantees because whereas they are not revealing their data to the central party, they're still providing model updates. And so through these model updates, the private information still leaks. So here, instead, we are providing privacy guarantees, whereas federated learning does not provide any privacy. And also the last point is that here, we're providing the querying party with labels rather than model updates, which means that the different parties can have different architectures locally. And of course, they can use the labels that they receive to improve their models and to even change the architectures of their models. So this is why we sort of coined the term collaborative learning to refer to this procedure. Okay, and so this sort of concludes the first three flavors of machine learning that I wanted to discuss. And so now you're wondering, why was this talk sort of titled 3 Flavors of Machine Learning? And we still have 10 minutes to go, but we're not done. So here, what I'd like to ask you is sort of whether we've sort of solved our sort of worries about privacy by introducing these different approaches that I've proposed. And so one thing in particular that I want to comment on is that in other areas of research on the security of machine learning, we've seen an arms race that is very similar to sort of other areas of research of computer security, where just like in the real world, there is work that needs to be done to balance sort of the cost of protection with the risk of loss, and you can't really break this arms race. And so I think here, the nice thing about machine learning is that it brings a paradigm that is sufficiently different from sort of these traditional computer systems that we can approach this notion of privacy in a principled way. And so what I'd like to do now is to illustrate why I think this is the case and why learning with differential privacy is so appealing, in addition to all of the things that I've already mentioned. One example that I like to give is to compare what we're doing in privacy with sort of the work we've done on adversarial examples, where we haven't found any way to defend against adversarial examples to this day. And one of the reasons is that if you look at a class of defenses, they're typically sort of providing empirical guarantees. And for instance, we've identified a large sort of class of defenses that provide something that is called gradient masking, where because adversarial examples are found through gradient descent, you can produce models that have uninformative gradients, but then an adversary can adapt to this by simply conducting a black box attack. So we, for instance, introduce transferability-based black box attacks, and those evade all of these gradient masking defenses. So now if we look at privacy, you can ask yourself a similar question. Because membership inference attacks exploit access to the confidence that the models predict, can I obtain sort of privacy by simply hiding the confidence away from the user when I predict? And so this is, again, something that has been proposed in many papers. The problem is that it doesn't work. And so the way that we showed that it doesn't work is by introducing a membership inference attack. And so this is work done by my student Christopher, where the membership inference attack does not need any confidence information. It's going to get a proxy to the confidence just by multiple queries on very similar inputs and observing the label that the model predicts on these very similar inputs. And so what Christopher found is that he can recover the same success, the same attack success here in the dotted orange line here, with only access to the label predicted by the model. And he can recover the same attack success than an attack that had access to the confidence predicted by the model. And so you can see here that the privacy leakage does not happen because you have access to the confidence. It happens because you haven't trained the model with privacy. And in fact, if we train the model with differential privacy, we found that it is the only defense that we evaluated that was robust against this class of attack, this class of label-only membership inference attack. And this shows, again, why differential privacy is so appealing, because it provides guarantees against adversaries that we have not discovered yet. Okay, and it shows that it is really bounding the privacy leakage because we're able to defend against these unknown attacks. And so are we done here? Unfortunately not. So because there are some variants of privacy that I haven't discussed today. And so this is the last thing that I wanted to mention in the last sort of 5 minutes that I have, is that there are some sort of concepts of privacy that are not covered by differential privacy and that are also not covered by the other flavor, which I guess is confidentiality, more of the crypto-like privacy. And so here, one example that I like to give is machine unlearning, where you might have, for instance, users that contributed data to your data set, and they later revoke your right to access this data. And so you're left with the question of what should I do with all the models that I've learned from these data points? And so this is something that is sort of motivated also, of course, by the recent developments in Europe, Canada, and California in terms of moving forward privacy regulations, introducing, among other things, the right to be forgotten. And so here it's very clear that differential privacy is not enough, right? Because what you're asking here is for the model to not learn anything about a specific individual point that you want to unlearn. Whereas with privacy, with differential privacy, you're bounding the potential influence of any point in the data set, and you're bounding this influence. You're not making it zero. So in some sense, what unlearning is asking for is for us to prove differential privacy with an epsilon equal to 0, which of course makes no sense because we cannot learn anything with an epsilon set to 0. And so this is sort of aggravated in the context of machine learning because machine learning algorithms, so training algorithms, are very stochastic in the way that you sample mini batches, the fact that the losses are very often producing non-convex problems because of the architecture of the model, and also the fact that the training itself is incremental. So once you've seen a point, all future updates depend on this point. And so it is really hard to define what machine unlearning should do. What we've done in a line of work is we've taken a very strict approach. And basically what we're asking for is a procedure, a training procedure, such that we can prove to the user that the distribution of models that we obtain by learning on data that includes their data point and then unlearning their data point is identical to the distribution of models that we would have obtained if we had never learned on their data point in the first place. So this is very strict. And so to obtain this, we've proposed an approach that is going to appear at the Oakland conference later this year, which is called CISA. And it basically improves on the naive strategy of retraining the model from scratch in two ways. The first way is that we shard the data. So this is similar to Pate, where we're going to, rather than train one large model, train multiple small models. And each of these small models is going to be faster to retrain, right? And so what this means here is that once we have a point that we want to unlearn, it's only going to be contained in one of the shards. And so we have to only unlearn, for instance, if the point is in the second shard, we only have to unlearn this second smaller model. The second knob that we introduce is slicing, which changes the order in which you analyze the points during training. So typically in machine learning, for instance, in deep learning, you analyze the entire data set in each epoch of the training procedure. And so what this means is, as soon as you complete one epoch, you've seen all of the training points. Here, we're slicing the data, which means that we're going to first train on, for instance, 10% of the data, and then save the model parameters. So save the state of the model, for instance, using the checkpointing mechanisms already in place in most frameworks. And we're going to save these model parameters before we introduce the next 10% of data. And then we're going to continue training now on 20%, save again the model parameters, and continue training on 30%, and so on. And so what this means is that once we get a learning request, we can revert to the last model parameter state that we know about that did not include this data point in the model updates. And then we can continue retraining from that. And so put all together, these two knobs sort of allow us to process unlearning requests much faster than if we had to retrain the model from scratch. And this is sort of a nice approach in the sense that it can work for any class of model. You don't have any requirement on the algorithm that you're using. And an interesting follow-up work would be to look at how we should shard and slice the data. We've looked in particular at non-uniform sharding and slicing, and this is interesting when you have some expectation of which points are more likely to unlearn their data. Of course, this introducing sort of fairness and ethical questions, because that might affect the performance of the model on these particular points. So with this, I'm going to conclude here. Hopefully we have a couple of minutes left for questions. And I want to finish on this optimistic note, which is that I think privacy preserving machine learning is an opportunity to make machine learning better. And this is best illustrated by the results that we've got on differential privacy, showing that once you have differential privacy, you have sort of very good generalization. And so I think this is very rare. As a computer security researcher, this happens almost never. Typically, we're introducing harmful sort of changes in terms of the performance. And here we're really looking at two properties that are very well aligned. And so I argue that this is sort of a very good motivation for continuing this line of work. And then before I stop talking, I just wanted to put the faces of my students up here to acknowledge all of their contributions to this work. All right, then I guess I'm done just on time. Hopefully we can spill over a little bit for a few questions.
Yes, thank you, Nicolas. That was a fantastic talk. I think you gave a lot of really nice insights on many interrelated issues. So I think that was really outstanding.
Thank you.
We have a couple of questions in the chat. So if you can look at the chat,
let me take a look.
Easier. Otherwise, I would have to read the questions as well. You may want to do that yourself. It's easier. And then we'll open the floor to other questions, because I'm sure people have a lot of questions here.
So the first question is, how do we?
1058. So it starts with in your analysis.
Yeah.
Do you see them?
So basically, I'm looking at the question. So I'm not sure I understand the question from David at 10:58 a.m. What I understand is that, so there are two things. Is first, the privacy analysis of Pate assumes that we only receive the label from each of the teachers. And so this is how we prove privacy, because this means that each teacher can only influence the histogram by ±1 vote. And so this bounds the sensitivity of the noisy argmax to each teacher's training data. And so if we start doing more than revealing the label of each of these teachers, then we have to change the way that we reason about the overall privacy analysis. And then the second part of the question, looking at sort of adversarial examples, data augmentations, this is what I showed in this. I guess I didn't have much time to describe it, but here what I'm showing in this graph is that data augmentation and adversarial examples are not a good defense against privacy attacks. And really the only line of work that we were able to measure significant improvement in terms of decreasing the privacy leakage was differentially private learning. And you can understand why, because differential privacy really imposes the worst case perspective on the privacy leakage, whereas every time you're going with empirical sort of adversarial example or data augmentation based techniques, you're getting more of an average case guarantee. So that's sort of the first part. Then we have a question from Borja. Could one have J? Borja, could you expand on your question? I'm not sure I understand the specific question.
Right. Yeah. So if you could go back to the proposal you have for this ICLR this year. Yeah, this one. So here you have just one querying party.
Yeah.
My question is if there.
Oh yeah. So yeah, no. So I didn't have time to mention this, but basically the querying party can alternate. So it can be any party that is participating in the protocol. It could be even a party that never participates as an answering party. So it's very flexible.
Okay, and in this paper you also study how having like subsets of parties that are all of those querying parties at the same time work.
So our implementation is specifically done for a single querying party in terms of sort of how we implemented the protocol. But it should be natural to at least you could repeat the protocol. And I'm sure there's ways you could do this sort of more efficiently than simply repeating the protocol. But we did evaluate sort of having alternate parties serving as the querying parties to sort of make sure that the gains that we're seeing are sort of consistent across different sort of subsets of the data distributions.
Oh, see. Nice. Thanks.
Yep. So the next question is, are you sure federated learning does not protect privacy of inputs by sharing model updates? So yeah, so federated learning does not protect privacy in the sense of differential privacy. It provides confidentiality in the sense of sort of the crypto definition of it, because basically the data is not flowing to the central party directly, it's flowing through the model updates. And so the model updates can be used to recover some of the sensitive features that are contained in the original data. If you wanted to obtain privacy with federated learning, you would have to combine it with a differentially private procedure. And so, for instance, you could train your central model with differentially private stochastic gradient descent and obtain privacy through that. But the privacy doesn't stem from the federated nature of the learning. The federated nature of the learning only provides sort of the confidentiality guarantee. So that's why I started the talk by saying that usually we use the word privacy to mean many different things. And so when you look at sort of the technical mechanisms that provide privacy, they come under different names. So confidentiality versus privacy is a very common confusion I find in a lot of work. And then in the last question, yes, for CAPC, basically the content provider, so the trusted third party, is indeed a central point of contact for all of the different answering parties. But the assumptions that we have to make are not as sort of important than the ones made by federated learning, because the content service provider sees a lot less information from the different answering parties. So it's only receiving labels. And so what we've done in our work is we've made assumptions that it's honest but curious. And we've showed that in that setting, it can only learn very limited information from the different answering parties' data sets. But I definitely agree that if we could come up with the same protocol idea, but without the trusted third party, and we're working on this, it would definitely help with making this easier to deploy. And then there is one last question from Jackie. Yeah, so when we use data to train a model, yeah, so there is a line of work that shows that, for instance, when you train models with one task in mind, so you train a model for instance, to recognize different objects in a data set, then it can extract features that are relevant for other tasks. For instance, there was some concerning results showing that you could use these features to recognize, for instance, gender in images. And so, yes, I think it's very hard to sort of characterize what information is extracted from the data by a specific model, because it extracts information that we did not sort of explicitly include as part of our loss, as part of the objective that we're trying to solve. All right, I hope that answers all of the questions from the audience.
Yeah, so people are, saying people are happy. So yeah, Nicolas, it was a really nice talk. So thank you again. I mean, I think you cover so much material, and at the same time, you were able to crystallize some of the key ideas. So I think that was really nice. So
yeah, thank you very much for having me over.
Oh no, that's our pleasure. We have a short break.